Um, I'm John Holbrey. I'm the School of Chemistry and Chemical Engineering at Queen's University, Belfast. I'm a long-term Sandals and Disordered Materials Group instrument user at ISIS, and I'm here to tell you something about the proposed Sandals-2 project. Where I thought I'd start actually was kind of looking at why we need to look at some of these aspects, and of course, we've just heard a lot of this already. That we have UK government commitments towards a net zero in emissions and economy as a target, and the target's getting closer and closer. So I've got highlights there of commitments to end emissions in 2050. That was signed into law in June 2019, and then April 2021. This has kind of been concertinaed to slash emissions by 78% by 2035, which is not that far away in this thing. And of course, one aspect of this is to look at what the UCRI, what our responses in terms of research portfolios, and the UCRI Energy Themes response is effectively to support the technology and the research that needed to develop energy technologies to address these challenges. And you can look at their the portfolio of projects that they're working on, and it's very, very diverse. At Queen's, we've kind of massaged this into looking at sustainability, as Ian was saying before, in terms of looking at green chemistry engineering, catalysis, recycling, efforts to achieve zero emissions in manufacturing. Of course, energy storage and generation, how do we actually produce energy in a clean and renewable way, and how do we store it for delivery? We're going to look at some aspects of that as we go along. CO2 capture, carbon reusage and reduction, plastics recycling, and generating functional materials through bottom-up engineering processes. I doubt anybody else's research portfolio is any different to this, however it's packaged. But this is, I think, is how us from the science and technology community are responding to the needs that we've been set by the government. So my job now is to really look at what we can do with Sandals, what we can do. I want to sort of show some highlights of the work that's been done with Sandals, and actually show how it can be done better with these proposed upgrades that we're talking to make Sandals-2. So I guess I have to start by saying where we are today. So if we look at Sandals as a disordered materials spectrometer, it was first commissioned and went into operation in 1989. So it's over 33 years old now. It's quite a mature and an old instrument. And apart from a brief down period in 2005 for detector refurbishment, it's been in operation over all that length of time. The reason it's still in use and it's still good is it is still the best instrument in the world for looking at hydrogenous amorphous materials over the short intermediate length scales. It's designed with low angle detector banks, reduces and minimizes as best as anybody has been able to inelastic effects from especially hydrogen rich samples, which gives us an amazing access to HD substitution, which from an organic chemistry perspective, from a water perspective, from a materials perspective, is really powerful to access multiple data sets and understand what's going on. And I have to say here that despite the building of Nimrod on Target Station 2, in terms of absolute resolution and performance, Sandals still outperforms Nimrod in the high Q, the short range order area, in terms of its performance. So it is still, despite being quite long in the tooth and aged, the best instrument for doing the job to date. However, along with that age, there's the things that are happening now which show that age a little bit. Measurements can be time consuming. Typically, it can be up to 6, possibly to 8 hours for a typical hydrogen sample to be measured. And I've got to note that actually Nimrod can count about 2 times faster than this on a standard liquid or disordered material sample. What that means in practice is that you're quite restricted we are quite restricted scientifically in terms of what can be done with the instrument these days in terms of the demand. And it's notable that, for example, experiments with a large number of samples, i.e. complex experiments that people are trying to do these days, there's increased demand for those to be performed on Nimrod in order to cut down the amount of time required to do the experiments. What this also means, notwithstanding anything else, is that if we could bring up Sandals to its full potential, then we do have the opportunity to actually allow the full capability of Nimrod to be used properly, the wide angle and the small angle neutron scattering in situ, by recovering abilities on Sandals. So what do I mean by that? That's kind of one of our science drivers pushing Sandals-2. This increased demand to study complex systems, and the examples I show you perhaps will illustrate some of the examples of what we're talking about in terms of complex multi-component systems where there's more than one component in there which can have isotopic substitution. And in one particular case, 42 samples were measured in one series of experiments, requiring multiple instruments, both Sandals and Nimrod, multiple allocations, beam time over a long period of time. That's clearly not practical as a way of demanding that much time on a single instrument if we want to expand our science portfolio. So let me look at what we're really going to get out of this, hopefully. The main part of this is the drivers for trying to get Sandals-2 are this demand for multi-component complex samples, including emerging solvent systems like deep eutectic green solvents, looking at electrolytes for batteries, thermal energy storage media, looking at catalysis and pharmaceuticals. Something that's been developing with Nimrod and we want to see more of on Sandals, which is the ability to do more complex parametric studies, looking at a range of temperatures or compositions, or the ability to do in situ and operando type experiments, which are not practical if it's going to take 6 hours per data point per sample at this current stage. So those are some of the drivers what we're trying to propose. So I guess I've got to tell you a little bit about what is planned in Sandals-2 itself. And the objective of Sandals-2 is to build on current front-end upgrades that are going on, will be going on through the shutdown on Sandals, to actually square off the pipe from the target station 2 to the instrument to actually go from a circular to a square pipe, which will give us actually an increase in flux of something like 60%, simply because by taking those edges, increasing those edges. We've got some objectives there, providing a new vacuum shutter and jaws, which will also increase flux. But these are effectively just going to brighten the beam. Okay, we want to do more than just brighten the beam that we're getting on sources. So the proposals for Sandals-2 really are to modify and advance the back end of the Sandals instrument to build on what's known and what we've got in Nimrod's capability. So we've got the ideas, the objectives are to basically replace the detectors with a full range of higher efficiency detectors encapsulated within a vacuum tank. So that's been learned from the Nimrod design to allow increased sensitivity, order of magnitude increase in signal to noise in the background. So it should get better apparent beam intensity and also much better signal to noise or signal to background ratios from this. This will lead to improvements for every single experiment that's run on Sandals. In addition to these capabilities, there's a proposal to actually put on a ring of 90-degree detector banks, which are kind of shown here on the schematic around the instrument tank, which will provide high angle resolution, which should allow some gem-like capability on Sandals to be able to look at things like hydrogenous, glassy to crystalline transitions, and perhaps be useful for things like looking at crystallization profiles or solidification of liquids into solids and transitions there. Overall, these proposed upgrades, both at the front and the back end, should give, and this is kind of the detail, up to a 5 times count increase rate, which effectively gives us some take-home things. It allows us to have a reduction from about 6 hours typically per sample at the moment, down to about an hour or a little over an hour, which really should enable either larger sample sets to be collected, time resolved or parametric studies to be done, Or the other side of this is much smaller samples to be done by focusing the beam, which gives a lot more access to expensive or deuterated components, or things that are simply not practical at the moment because of the scale that we have to operate at with a standard 30 mil Tizer cells, for instance. So there's a lot of opportunities here, which we can discuss in the breakout, for developing better and more chemistry and more science from these upgrades. I want to show you for the last 5 minutes or so some of the work that's been done on samples to date and how I can show it's brilliant, but it's opportunities for being even better through these upgrades. For example, looking at water as a fundamental functional material. Work in the past, so Lorna Duggan, who's going to speak in one of the other sessions, with Alan Soper, looked at basically at hydration in metal ion solvates, which would just be a standard parametric study, except that this had implications for the presence of liquid water in Mars. So it gives a context and highlight outside of simple science. But the developing of the knowledge of what we can do with water has got real importance for energy and for clean technologies. For example, work from Neil Skipper, recently looking at gas hydrates, which links into our current petrochemical gas supplies, but also helps us explain how hydrates and clathrates are formed, which can be relevant to things like CO2 capture and storage underground, and how these work. Now, I color-coded a few of these slides. So the orange box is something that may or may not be potentially useful in the future. An area of importance, I think, for energy storage is things like thermal energy storage with phase change materials. And one that's particularly important in industrial terms and in civil engineering terms is sodium acetate trihydrate, which again, of course, is just a hydrated molten salt. To study this, and we have collected recently some data on this system, and understand what's going on, you clearly need to look at a lot of energy, a lot of different terms. We got a complex material, which has both acetate anions, water, and urea as potential deuterator sites. And you might want to look at both composition and temperature, and also potentially go from a liquid through to a solid in terms of your behavior to understand what's going on. So the demand to actually look at something like this really requires more throughput and ability to actually collect a lot more samples than we can do at the moment, something that can't be done with 6 hours per sample. I've tried crystal ball gaze on this and to look at other people's work that's not been looked at in this way. And again, in terms of thermal energy storage media, work in Australia has been looking at a range of salts. So these are molten salts or salts that melt, and they're interested in looking at thermal energy storage by understanding the hydrogen bonding patterns in the crystal state, crystallizations in the crystal stages. But clearly it would be useful to look at the liquid and the liquid to solid transition and see how the interactions are going on there. If this work was followed, you're looking at a range of different materials with a range of different deuteration patterns that would be needed. And of course, again, tracking through temperature studies, which require faster data collection and consequently a lot more beam time allocation than would be available at the moment. I want to look at just a couple more areas of opportunities that will come out from Sandals-2 here. So one of the areas that Sandals has been fantastic with has been with the growth of ionic liquid chemistry over the last 20 years. And I've got some pictures here of which identify some of the areas that are useful of these novel liquid materials, both in energy storage, electric catalysis, and actually one from a manufacturer in Germany suggesting uses in space in other areas, including batteries, thermal management, gas separations. Let me show you what I mean about what we can do, what has been done with ionic liquids with Sandals. The first organic ionic liquid was studied back 20 years ago on Sandals and identified the capability to use the hardware, the Sandal instrument, and the software, if you like, EPSR, to understand and study the structure of these new materials. Data still coming out, fundamental data about ionic liquid materials. For example, from Rob Atkin and Ralph Ludwig, collaboration between Australia and Germany with ICIS, looking at hydrogen bonding interactions between different functional components in a different ionic liquid. And again, you can see a typical experiment requiring 7 different isotopic substitutions, where they're looking at substitution on the ring, on the alkyl chain, on the hydroxide group on this particular material, and to identify what's going on, which is, again, does not have trivial deuteration. It requires quite a lot of work there in terms of from a chemistry perspective. Why are these fundamental things important, I think? And this is looking about potential for the future. So this is things I'm not really, so back at the time we were looking at the first ionic liquids that could be used, that could be understood with ICIS. We're also looking at identifying uses of the ionic liquids, and one was to dissolve cellulose, so being able to access biomass in a clean and effective way. And again, later on at Sandals, experiments we've done to look at the modes of dissolution of actually glucose as the monomer for the polysaccharides in cellulose, to understand the role of the solvent, the ionic liquid, in this dissolution process. And why is this relevant? Because there's lots of things going on in this field in terms of green, sustainable energy and materials. For example, 4th generation, if these are 1st generation, 4th generation ionic liquids have been used as excellent solvents these days to convert wood and waste cottons into high quality fibers, both for fabrics, but also for ballistic cottons at the University of Aalto. And this is on target for commercialization. It's a different ionic liquid. Can we prove it works? How it dissolves the materials? We don't know. This is something for the future. Additionally, at Imperial College, a different ionic liquid, a very simple sulfate salt, was shown to be an absolute rubbish solvent for cellulose. But conveniently enough, it was found to be an excellent solvent for dissolving the lignin component of biomass to access cellulose, to enable it to be used for glucosylysis to glucose for conversion to ethanol and other energy products. How does it work? How does it dissolve things? Well, we don't know with that one, but work has gone on at ICIS to study some aspects of this. So in a different ionic liquid solvent has been looked at as a solvent solubilization of guaiacol, which is a lignin derivative or a lignin model. This is work actually from Rob Atkin and Greg Waugh in Australia. And you can see 12 samples were studied, 4 different independent hydrogen deuterium components in the system, both the cation and the anion of the ionic liquid, the guaiacol and the water. So you've got a wide combination of deuterations that needed to be done to deliver the system. I'll show you, I think, just 2 more slides to finish because I realize I've gone on too long. The 42 samples that were run to understand how an ionic liquid water mixture transfers from being water dissolved in the solvent to the solvent dissolved in water. 42 samples, a massive amount of work that was done. If this was done with 1 hour per sample, it could be done in a much more realistic time frame to get this important data. And this was noted as an Angevin paper, very important. So it's reflecting the importance of work in ICIS. We could talk about this in breakout session, people. I want to show you just the other aspects, not just liquids. The upgrades that proposed for 90-degree banks should help looking at things like hydrogenous solids, for instance, catalysts, and this is the work of Stuart Parker and others, combining Sandals data with a range of other facilities, spectroscopy. And also, as we said before, parametric studies, the ability to do some, in situ experiments, the ability to do something like these experiments I've done on Nimrod, first of all by Chris Hardacre and then Gladden, looking at modeling hydrogenation reactions where, okay, in this case, it requires to look at the porosity and support, but actually most of the information, the detail they want is in the Sandals region and the resolution. But this experiment could not be done on Sandals because this real-time in situ probing can't be done with the current count rates that we have. They've expanded this to look at a range of clever things, including instrumentation with this system where we can also look in situ at the neutron scattering, but also have an NMR probe in the beam. This is kind of I think, an amazing piece of kit that's been developed to get extra information in parallel with the standard neutron experiment. And again, they can study, you can track the reaction, the hydrogenation reaction in real time, something that can be transferred and hopefully brought into looking at catalysis and other absorption experiments on Sandals. That's me. The most exciting thing, I think, is this increase in effective brightness on the instrument means we've got these opportunities to reduce experimental time significantly. And I think the community is crying out for this, or also to access much smaller samples of very challenging isotopic compositions to allow a much broader range of experiments to take place. And I think that's a really big opportunity for the future. Okay.